Hi folks, my name is Joe Salisbury from University of New Hampshire. I've been asked to talk a little bit about linking optical measurements from space to biogeochemical products and also tell you a little bit about NASA's newest Ocean Color mission. I want to thank my colleagues on the GLIMR mission, in particular Antonino Mannino from Goddard. And also I want to mention that I lifted several slides from Jeremy Wardell's presentation given here last year. So let's start. So ocean color, the color of the ocean is determined by the interactions of incident light with the substances or particles present in the water. We see this surprise little photon that enters the water, and there are photons that several photons at different wavelengths that enter the water, interact with the water and with substances within the water, and a small fraction of them are scattered, back out of the water towards the sensor. Now, ocean color data refers to accurate measurements of the light intensity at several visible wavelengths. Okay, so what does a satellite see? Well, a satellite might be looking down on varying water masses. Here's a bunch of different water types from crystal blue waters into phytoplankton blooms and sediment-laden waters that you'll find inland and inland lakes. And here's what we're looking at, or what the sensor is looking at. But here's something like what we will see when we get the data from that sensor. So the sensor gathers information and returns data that produces, parts of curves that look like these. And what we're seeing here is water leaving radiance, probably normalized leaving radiance. And you'll notice that each spectra each spectra is different for each water type that we are looking at. And you'll see there's a great deal of signal in the blue in the bottom panels, but much, much less signal in the blue on the top panels. Okay, and so I say it gathers information on parts of these spectra, and that's problematic. So what we're seeing here now are four of the sensors, the US sensors, the two on the right, Modus and Beers, are in space now. The previous two have served us well, but they are now retired. And you see the colors there, those colored bars are the bands, the wavelengths at which they gather information. And so it's certainly not a full spectra. So these spectra have been placed fairly carefully to get information about pigments and particles and enable us to do atmospheric corrections, which I won't talk about, but are a challenging and important part of getting water leaving reflectance or radiance, remote sensing reflectance, etc., from which we generate most of our products. Okay, so what we get is something that looks like these spectra here, are parts of these spectra, but what we want to get at are the things that are in this spaghetti diagram. This is from a new paper by Bruin et al. That just came out a month ago or so, and I don't expect you to take much from it, but I will say that there are several different pools of carbon in here that we'd like to know about. But then there's also the wiring diagram. These are the rates, the photosynthesis, the respiration, the sinking, the export. These are the things we'd like to bring to bear, or bring satellite data in to help us understand some of those rates as well. So let's look over on the left here at the biggest carbon pools in the ocean. The first one is dissolved inorganic carbon. Dissolved inorganic carbon is by far the largest pool of carbon, but it's invisible to sensors, and we really can't understand too much about it except how it's perturbed by processes that we can see. Like we can understand something about photosynthesis that consumes DIC, for example. Okay, next we have DOC. Part of that is colored, and that's good news because we can get information about the colored fraction of the DOC, and it's an important large pool, and we've come to understand a lot about the dynamics of DOC from satellite studies. The next is POC, which you'll notice in the number here, 2.3 petagrams carbon, is a relatively small number, but we can use satellite data to understand phytoplankton distributions quite well, as most of you know. And this is a small pool, but it turns over very, very rapidly. And it's what's responsible for taking carbon out of the atmosphere through the living biosphere, and then what's exported away from the atmosphere on century type time scales. And we can even understand something about PIC, particular inorganic carbon. That's calcite bearing organisms, which is also a small but very important part of the carbon cycle, particularly at very long geological type time scales. Okay, so we've got this right here, these spectra, or parts of these spectra. And what we want to get at are these stocks here. These stocks like chlorophyll, suspended sediments, dissolved organic carbon, POC and PIC. Okay, and to do that, we have to invoke some mathematical equations to take that information from the spectra. And historically, we've used these band ratios, which has served us well for nearly 30 years right now. They're very simple, economic, computationally economical, and fairly accurate for certain products. Okay, but we can also take a semi-analytical approach, which is much closer to optical theory and optical closure. Here we take these apparent optical properties, basically what the satellite sees, to model inherent optical properties, those properties that are inherent to the substance of interest. And from there, we can relate these to the constituent that we're trying to retrieve. And the new sensors that are coming out now, particularly the hyperspectral ones, are relying on semi-empirical approaches to get at these inherent optical properties. And then, if you do a Google Scholar search on machine learning and ocean color, for the last 2 years, you'll get over 10,000 hits on that. And so there are new techniques that are being developed. This whole discipline of artificial intelligence, where you feed it in data in your computer, and the software will generate the best relationship between those data and the product that you are trying to get. And exciting new work in the algorithm front with machine learning. Okay, so we're getting good at getting the stocks for sure, but what about the rates? A rate is it changes over a distance, or it changes over time. And these rates, I mean, isn't that what the global Earth science modelers really want? Don't they need to know the amount of carbon being fixed that comes into the biosphere on some time scale? The community respiration, that part of the fixed carbon that is being consumed at shorter time scales, the export production, the net calcification. Yes, we want all these. And it's challenging because right now we don't have information, very good information about the time step. Satellite data is supposed to be every couple of days, but in reality, it might be weeks before we get subsequent determinations in the same spot on the planet. So it's really difficult to know how these stocks are changing over time. So we have to model in, some information about time for net primary productivity. For example, you might take a parameter like maximum photosynthesis, which is the amount of carbon fixed per time. And they might be able to parameterize that with satellite data. But this is often the biggest error term in these primary productivity algorithms. So this is a challenge. We need better models and more timely satellite data. Okay, now we can get partway there to understanding these rates if we know something about particle size, distributions, and biodiversity from space. That will help us get partway there. Okay, and the reason is because if we know something about the community that is doing the production, their size or their species, they work at different rates and they're sensitive to different environments. And so there's this great paper by Kostadinov that came out in 2009. It's getting kind of old now, but it's still well cited. And they used CWIF's data, I believe, to come up with satellite determinations of particle size. And here's one example from the paper where they have showed nano-sized particles on the left, the actual concentration of them, micro-sized particles on the right. And so presumably, these different communities would have different productivity rates. And so you get much closer to understanding these rates that we want to know. Another way to do this is to take advantage of the pigment properties. And so pigments absorb differently at different wavelengths, and different species have different ratios of different pigments. Here on the left, we see some work by Tiffany Moisen et al., and she shows the absorption of several different pigments that are found in phytoplankton. So, if we could take a satellite now and hyperspectrally retrieve that absorption information, I think you can see where we could get a lot closer to understanding the community and maybe understanding more about the rates that are important. On the right, we see 4 different species of phytoplankton, but here Ryan Vandermeulen has also put in the wavelengths or the bands of the MODIS sensor. And you can see that a lot of these bands are positioned quite nicely to pick up quite a bit of information about these different curves, but it's certainly not perfect. For example, we don't see any, this big information difference in the UV, that 360 to 400 or so, and we don't get any of that with MODIS. And then there's these other articulations in the spectra too that we lose information on it. So the hyperspectral data should help. Okay, and so, well, what do we get from moving from multispectral satellites that are up in space right now to the hyperspectral ocean color sensor like PACE? Well, we get a lot more. We can understand this phytoplankton physiology and community composition much better. You'll see up in the purple here, we get some information on absorbing aerosols. We've never had good information about those from ocean color sensors. They're an important part of the atmospheric correction that we need. And there's so much more that we can understand about particle size distribution and fluorescence if we have these bands that are narrowly spaced and lots of them. And one example that Jeremy had in his presentation, I want to show it again, is up on top. I believe this is work by Joachim Goes, but up on top, this is what MODIS would see in 2 different phytoplankton species. One is Noctiluca, which is kind of a nuisance giant phytoplankton, I believe. And the other one is a typical diatom. So they're pretty close, except in this one area here in 550. But if you look at this hyperspectrally, you see this big area right here. So you might be able to discriminate them from hyperspectral data, but it would be a challenge from multispectral data. Okay, so now a quick shout out, like we should all give, hail to the arrival of PACE coming to a low Earth orbit near you. PACE should be a game changer for the ocean science community. Not only is it hyperspectral, but it will be really high quality data, high signal to noise. It flies with other sensors, including 2 polarimeters that will give us a lot more information about the aerosols we need to make better ocean color data. So this is tremendously exciting development that's happening, being launched in just a couple of years or so. Okay, so what if we add the element of, what do we get by adding the element of time to hyperspectral data? So here, imagine that we have hyperspectral data, but we get it every hour. So now we get to study so-called fast processes in the ocean. And you know, if you think about it, well, what does that mean? So if you think about it, one of the most profound geophysical signals that a phytoplankton community will see is that daily sunrise, you know, sun moving across the sky, and sunset. And we know from lab studies that these phytoplankton, you know, migrate up and down. They change their carbon to chlorophyll ratios as the sun gets higher. They do all kinds of unusual things over these time scales, but we haven't been able to study that very well with satellite data because of this. We don't have the combination of hyperspectral data every hour. Okay, so by adding the element of time to hyperspectral data, we can also check trajectories. We can also see where things develop, where they're moving to, where they decay away. We can follow oil spills and HABs and whatnot. So it's an exciting development. And so I'm going to end here with a few minutes on the NASA geostationary literal imaging and monitoring radiometer, GLIMR. And it's NASA's newest ocean color mission, and we intend to launch in November of 2026. I'm the PI, and Antonino Mannino is the deputy PI. Raytheon Aerospace is the designer and builder, John Macri from UNH's project manager, and Southwest Research Institute is mission assurance specialist on that. So GLIMR is going to be a hyperspectral radiometer. It has a spectral range from 340 to 1040 nanometers with fine spectral sampling. It has a nadir resolution. This is going to be in a geostationary orbit, probably around 95 degrees west. So it'll be somewhere over Ecuador or something. And it's going to be looking down at the continental or the oceans of the CONUS, and also in looking down over South America as well. It's going to have a 300-meter nadir resolution. We're primarily interested in processes that are going on in the Gulf of Mexico with all the river discharge, the HABs events that have been occurring, and the nuisance algae. And so we think the Gulf of Mexico is a good place to focus on. And it's a relatively small instrument, low power instrument, and it's on a 2-axis gimbal, so we can steer around. And so if there is an event in the North Atlantic that's tremendously exciting to the science community, we have the capability to come off mission for a while and study that at very, very high temporal and spectral resolutions. Okay, so very quickly, I want to show you where GLIMR can see here. This is a measure of something called the air mass fraction. Basically, the red dot is where GLIMR's orbit is, and the yellow dot is the sun. And the blue areas is where we can image. Okay, so as that comes around right now, you'll see, okay, coming up right now, we're over the Gulf of Mexico. So we're going to really focus on the Gulf of Mexico during this time. But you can see that later in the afternoon, we're away from the Gulf of Mexico, and we can really focus on the Pacific and the West Coast of the United States. Likewise, in the early morning, we can focus on the Amazon plume. So that's going to be our strategy. Focus on the Gulf of Mexico, but get a lot of other interesting areas as well. Okay, so here's a slide about our cartoon, about the processes that we study. And so we're primarily interested in this transformation of phytoplankton, its physiology, its bloom evolution, but we're also interested in discharge, coastal emissions, things that happen over really short time scales. Okay, and so we would like to investigate how these high frequency fluxes of sediment, organic matter, and other materials between and within the coastal ecosystem regulate productivity. Okay, but we also have applications, and NASA demanded this of us when we put in the proposal. And we're going to like to target the formation, magnitude, and trajectory of harmful algal blooms and oil spills. Okay, and so we brought in people on our science team that study, oil spill thicknesses, oil seeps, oil spill extent, and also folks that study harmful algal blooms that cause damage to ecosystems and indeed human health and property values too. And particularly we're interested in the dinoflagellate Carina brevis. So we have these real specific applications. We have application specialists. Maria Georgiou is leading up the applications team for GLIMR. And we want to get these products out so that they can be used by society. Okay, and so let me conclude right now. In the current status of GLIMR, we just started officially. We've been working on a contract for well over a year. Our partner Raytheon is conducting internal engineering analysis and design trades to make sure that the instrument that we design can do the science that we need. And we're a cost cap mission. It's very challenging. So we have our first major review in October. In that time frame, we have our systems checkout, ready to ship on in August of 2024 and launch that in 2026. So I just want to say that this is going to be a new opportunity to do different science, to think a different way about using ocean color data. And if you have ideas, please get involved after this summer. We're getting things ironed out right now, but we're looking for ideas and interests. So please contact me or another GLIMR team member. And thank you very much for listening.